Okay, so this is a short screencast about the beginning of the material in pre-calculus. Today, we'll try to cover certainly the first section and some of the second section in chapter 1 as well. So pre-calculus is, as the name suggests, the precursor to calculus. In calculus, the atomic objects that you work with are functions, much the same way in elementary school. The atomic objects you work with in math are numbers. So when you are young, much of your study of math is learning how to combine numbers, how to manipulate them, how to use them, understand them, and so forth. We will do the same in this course for functions, which are more complicated objects, to be sure, than the numbers. So our first chapter will be sort of a general overview of some of the basics of functions. And that will occupy us during the first week of the course about. And then after that, going forward, most of the rest of the course will be a sort of tour of various important families of functions and trying to understand them and talk a little bit about how they are applied. Okay, so to get started, we should say, what is a function? And a function is nothing more than a rule. A good way to think of a function is it's an input-output mechanism. So a function takes an input number, it does something to it, and produces an output number. Now, there are lots of things that you can do to an input number, so there are lots of different kinds of functions. One little caveat here is you can't assign an input to more than one output. So functions are deterministic. They don't sort of flip a coin and pick from a menu of outputs. If you give a particular function the input 4, it always produces the same output for that input. So here are a couple of really simple examples of functions. The doubling function is the function that doubles its input. So again, the important thing here is this function is a rule. And the rule is you give me an input and I double it. So the first challenge we have is how do we sort of express that? Because it's clunky to express it in a sentence, especially if we want to talk about functions more complicated than this one. We might do something like this, right? So this indicates that the input 2 goes to the output 4 because 2 times 2 is 4. The input 3 goes to the output 6 because 2 times 3 is 6, and so forth. And that's a little bit better, although again, this is still a little bit unwieldy as a notation. Another example would be something I'll call the +5 function. So this rule is a rule that takes an input and adds 5, right? So that's all it does. So if you give me the input -6, I add 5, -6 plus 5 is -1. You give me the input 0, the output is 5, 0 plus 5 is 5, and so forth. So that's sort of the idea. And of course, there are all sorts of things you can do besides double and add 5. You could triple, or you could subtract 10, you could double and then subtract 10, et cetera, et cetera, et cetera. So there are lots of different kinds of functions that we can invent. A quick bit of terminology: a function is one-to-one if no output is mapped to by more than one input. Now, every function never generates more than one output for a given input. A function can, however, take 2 different inputs and map them to the same output. That's allowed, but it's not one-to-one. So we'll circle back to this terminology as we go forward. I just wanted to introduce it here at the beginning. So here's another example, the squaring function, right? So this is the function that takes its input and squares it. So if you give me the input 2, I produce the output 4 because 2 squared is 4. If you give me the input 3, the output is 9 because 3 squared is 9. This is a good example of a function that's not one-to-one, because you can see if you give me the input -3, -3 squared is 9, and +3 squared is 9. This is still a perfectly legitimate function. Functions can do this. You can have many inputs assigned to the same output, but it's not a one-to-one function, right? So one-to-one functions don't do this. Okay, so as I said, the first thing we need is this kind of a better way to express functions than using sentences or long strings of connections like this to try to get a pattern across. In math, we like to use very short, compact notation. So function notation is going to be our answer to this problem here. What we'll do for the doubling function is usually instead of writing all these arrows, we'll give the function a name. So we could name this function D for doubling. And the name is most often a single letter, right? We try to abbreviate as much as possible. And we'll write an expression like this that's highlighted in blue to mean that this function takes the input 2 and maps it to the output 4. And the way you read that blue highlighted thing is D of 2 equals 4. It's important to realize that this left-hand side, that's not multiplication. It's not D times 2, it's D of 2. What we're doing is we're taking the input 2 and plugging it into the function named D. So similarly, D of 3 is 6, right? 3 doubled is 6, D of 10 is 20, and so forth. And for a simple function like this, we could use a variable input as a way to very compactly communicate the function, right? So this says that our function D takes an input X, and the result is always 2 times X. Notice that the input letter doesn't play much role. This function right here that's highlighted in blue is exactly the same function as this function. We just decided to use a different letter for the input variable, which doesn't affect very much. For the +5 function, I think that comes next. Maybe we'll call it PF for +5, or you can use whatever symbol you want to denote a function. +5 of -6 is -1, +5 of 0 is 5, and so forth. And here the formula is +5 of X is X plus 5. Okay, so generically, a lot of the time in textbooks and such, we're talking about sort of an abstract function that we've just kind of invented. And often the mechanics of it are too complicated to describe nicely with something like doubling or squaring or +5. Books often use the letter F for function as their name for a function. So they'll use letters like FGH to symbolize functions. Usually we'll use X as the input variable and Y as the output variable. It's important to emphasize that this doesn't really matter. It's just a convention. And I mention it just so that you're sort of used to it. And when you see X's and Y's, you should be thinking X is probably the input variable and Y is the output variable. And again, we read this Y equals F of X. All righty. So again, yes, X is the input number, Y is, whoops. There we go. X is the input number, Y is the output number, and F is the name of the function. That's how to sort of interpret all of the symbols in an expression of functional notation like that one that is highlighted in blue. So what comes next here? So here's an example that is a little bit more applied. The number of fish, bass in a lake is a function of the number of years since the lake was stocked. So here we have 2 variables that are specified quantities. One variable is the number of years since the lake was stocked. The other is the number of bass. And a natural way to think of things here is that the latter, the number of bass, is a function of the number of years. So we could use the letter B to represent the number of bass, the letter T to represent time, the number of years gone by, and we might write B is equal to S of T. So often when we have variables that have meanings, like here, number of years and number of bass, we'll use different letters to kind of evoke the meaning of the variable. If we're just talking about some abstract formula, we'll often default to something like Y equals F of X. So yes, again, this is just an explanation of what I just verbalized. T is the input variable, number of years. B is the output variable, the number of bass. And so notice that in this context, a sentence like this one that's highlighted in blue, so this means that when you give the function S the input 9, the output is 1200. Well, here the input is the number of years since the lake was stocked and the output is the number of bass. So this sentence means that 9 years after the lake was stocked, there are 1200 bass in the lake. When the input's 9, the output is 1200. Likewise, this sentence, right, very similar structure, says that 20 years after the lake is stocked, there are 4,200 bass in the lake. So here we don't really have a formula for S of T, just kind of a context for it, an understanding of what it means. And a problem in statistics that we won't talk a lot about in this class is in a situation like this where you might have some data for the number of years and the number of bass. Can you come up with a formula that sort of captures this function well? Again, that's mostly not a topic for this class. Okay, so one way to express a function, there are sort of three main ways to express functions. A sort of numerical way using input-output tables, a visual way using graphs, and an algebraic way using formulas. Let's talk about each of these, and that'll be good for this section. So this is what an input-output table looks like, and this is an input-output table for the doubling function d. And all it is a table with two rows. You could make this vertically and use columns instead of rows. It doesn't really make much difference. One row is for the input, x. One row is for the output, d of x. And I just sort of lay out a bunch of inputs. What inputs I use kind of depends on what I'm trying to communicate with the input-output table. And below each input is the corresponding output, right? So below 4 is 8, because when you plug the input 4 into the doubling function, the output is 8, right? Similarly, d of 6 is 12, and hence the number 12 is below the number 6. Here is an input-output table for the +5 function. I've just picked a few random inputs here. And you can see that right below them are the corresponding outputs, right? So if I plug the input 7 into the +5 function, I get the output of 7 + 5 = 12. So these kinds of tables, these can be useful ways of communicating functions. It's a sort of more numerical, data-driven look at what the function is doing. Here, by the way, is an example of a table. I won't even call it an input-output table, a sort of two-variable table for a relationship between two variables that's not a function. And it's worth noting that two quantities, generically x and y, can be related in lots of different ways, including many ways that aren't functional relationships. This isn't a functional relationship because of the yellow highlighted columns, where you can see that the input 2 is assigned to two different outputs, 8 and 3. So there may be some connection between these two variables, but it's not a functional connection. And in this class, we're not much concerned with relationships like this. We are concerned in this section with being able to identify when the relationship is not a functional relationship, as we've done here. And finally, here's an example of an input-output table for a functional relationship that's not a one-to-one functional relationship, right? And this relationship's not one-to-one, again, because of the yellow highlighted columns. I have these two different inputs, -3 and +4, both assigned to the same output. It's okay for a function to do that, but it's not a one-to-one function if the function does that. So that's something worth bearing in mind. One-to-oneness is important for when we start talking about inverse functions. Functions that aren't one-to-one don't have an inverse, but we'll get to inverses later. Okay, so that's input-output tables. A graph is a way of drawing a picture of a function. So here's a sort of picture of the doubling function. And let me grab this input-output table here just to talk about a little bit where this comes from. When we draw the graph of a function, we will agree that the input variable goes on the horizontal axis and the output variable goes on the vertical axis. That way we're kind of all on the same page when we graph functions. And so if I have an input-output table for a function like this, what I really have is a lot of different ordered pairs on the graph of the function, right? Input is the horizontal or x value. That's why we usually use x as the input letter. And the output is the y value on the graph. So this input-output table says that the pair 1, 2 is on the graph. And that is this dot right here where the cursor is pointing. This pair says that the 0.24 is on the graph. That's this second dot right here. And if I have an input-output table like this, I can generate a whole bunch of dots on the graph. If I connect the dots, I get a sort of image of what the function what the function is like. Most of the functions that we encounter, and we'll talk more about specific graphs as we go, have a very sort of definite shapes. So we won't have to graph tons and tons of points. We'll be able to sort of know what they look like just based on a few points. But for now, I just wanted to sort of understand where the graph comes from and what the connection is between the graph and the input-output table. And here is a few points on the graph of the +5 function. And here again, I've just used this, let me pull this down here, this input-output table and plotted the points that are in this input-output table, right? So you can see, for example, that pair 2, 7 corresponds to this dot where the cursor is on the graph, right? The X value is 2 and the Y value is 7. If you take a relationship, if you take a graph like this, like take this blue graph, now this is a graph. I mean, any picture in the XY plane qualifies as a graph, but not all graphs are functions. And this graph is not a function because at this input value, and again, the inputs are always on the horizontal axis, you can see I have 2 output values for the same input value. And on a graph, you can spot this because a vertical line will clip the graph in more than one place. If this happens, then the graph is not a function. So we have a really nice way of telling when a graph is not a function by using something called the vertical line test, right? If a vertical line hits the graph more than once, then the graph's not a function. Similarly, here is an example of a graph. Now the blue curve here is the graph, the blue curve. This does look like a function. It looks like it passes a vertical line test, but it fails what we call a horizontal line test. That is, if I draw this orange dashed line, you can see it hits the graph in 2 different places. The significance of this is I have 2 different inputs, and it looks like about -2 and +2 are those inputs that both get assigned to the same output. This is fine for a function, but it's not a one-to-one function. So this is the sort of visual analog of what we were seeing up here in this input-output table, where we have 2 different inputs assigned to the same output. So 3 different ways of sort of dealing with functions. We've talked about 2 so far: input-output tables, there's an input-output table, and graphs. The third, and the one that is maybe the most important, although the other 2 are important as well, is using algebra, using algebraic formulas. And we sort of hinted at this already, right? With the doubling function, we computed a number of outputs, and we noted that a general formula for this function is the function d of x is equal to 2x. So this means, right, that I can now compute the function output at any input just using this formula. So this is a powerful way of communicating the rule, because in a really short, sweet formula, I'm able to communicate the entire rule. And now I can apply it to any input, right? D of 23 is 2 times 23. Notice that functions are very mechanical. Whatever you give this function as an input, it will produce the output 2 times that input. You can feed it numerical inputs like 11 and 23. You could also feed it a variable input like p, and it will just keep doing the same thing. It does 2 times the input. You can even feed it some complicated algebraic expression like a plus 3b, whatever that means, and the function will just multiply it by 2, right? It always does the same thing. The output is 2 times the input in this particular case. Similarly, for the +5 function, right, we wrote that down above. That's the formula. And again, this allows us to compute the function value at any input, right? +5 of 9 is equal to 14, +5 of t is equal to t +5, +5 of +5 of a squared, right? Again, the function doesn't really care what you feed it. It's always going to produce the output of input +5. So +5 of a squared is a squared +5, whatever that is. Okay, so let me talk a little bit about the second section, and then for the couple folks who are here, I'll say a little bit more about these exercise things. Okay, so domain and range of a function are the topic in section 1.2. I think that we'll just get partway through this today and leave the rest for tomorrow. First, a word about how to express sets of numbers. So a set of numbers is a collection of numbers. Here are a couple examples, right? So this first thing is the set that contains three numbers, the number 5, the number 9, the number 13. And all I do is I use curly braces to enclose the set, and I just separate the numbers by commas. And this method works even for some infinite sets as long as there's a pattern, right? The set of all positive even numbers, 2, 4, 6, 8. I can get that across using my curly braces. I list the first few, and I use an ellipsis, a dot, 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 when the pattern is clear. So this is all well and good for some sets, but most of the sets we care about won't be able to be conveniently expressed in this way, because we are mostly interested in sets that are intervals or combination of intervals. And an interval is a subset of the number line that is connected. And you'll notice that these sets aren't connected in the sense that if you take this first one, the number 5 is in the set, the number 9 is in the set, but 7 is between 5 and 9, and it's not in the set, right? So that set's kind of not connected. Likewise here, 2 and 4 are in the set, but 3 is not in the set, right? So the set's not connected or continuous. We can have stick with sort of intuitive understandings of those words, connected and continuous. We don't need to be too precise about it. So an example, I think we're coming to, the set of all numbers between 2 and 4. Now, notice this is not just the number 3. It's also the number 2.4 and 2.671 and 3.04916 and pi and so forth. There's infinitely many numbers between 2 and 4. We're not just talking about integers or sort of nice round numbers here. So one way to express this is using a similar notation to up above with the curly braces on the outside, but I'll use a variable to get the idea across. So the way you read this is the set of all numbers x such that x is between 2 and 4, right? Bigger than 2 and less than 4. And because I said strictly between, I want strict inequalities here on either side of the x. And this is a good way of getting across this interval. And this is an interval because I want all the numbers between 2 and 4. We'll also use something called interval notation, which is an even more compact way of getting the idea across. We'll just write 2 and 4 with parentheses around them to express all the numbers strictly between 2 and 4. Now we have to be a little careful because that blue highlighted thing looks a little bit like the coordinates of a point. And so it'll have to be clear from context whether we're talking about a set of numbers or a point in the plane. And a couple of other examples I think will make this notation a little bit clearer. What about if we tweak this set a little bit and talk about the set of all numbers between 2 and 4, but also include the endpoints 2 and 4 in the interval, we don't want to use the same notation for that because it's a slightly different set. If we use set builder notation, which was this one here, that's not such a big deal. All I have to do is adjust my inequalities to be loose inequalities instead of strict inequalities. In interval notation, what we'll do is instead of using parentheses, we'll use square brackets, right? So this is an important distinction. The parenthesis means that that endpoint is not included in the interval. The square bracket means that the endpoint is included in the interval. Intervals with parentheses are called open. Intervals with square brackets are called closed. Intervals can be half and half, right? You could have a set of numbers between 2 and 4, and maybe you want to include the left endpoint 2, but not the right endpoint 4. In this case, again, in set builder notation, it's not a big deal. We just adjust the inequalities appropriately. So here we would want a strict inequality on the right and a loose inequality on the left. In interval notation, we'll just mix parentheses and square brackets appropriately, right? So we use a square bracket for an endpoint that's included and a parenthesis for an endpoint that is not included. And we can use this methodology to talk about infinite intervals as well. For example, the set of all numbers bigger than or equal to 5. Again, I mentioned this before, but just to repeat, this is not just 6, 7, 8, 9. It also includes all the decimals, right? Like 6.4 and 7.52 and so forth. In set builder notation, again, not a big deal, right? Set of all x such that x is bigger than or equal to 5. In interval notation, it looks like we're sort of missing an endpoint here, but we can use infinity to get the idea across, right? So this is the interval from 5 to infinity. This just means everything bigger than or equal to 5. So there is no upper endpoint. Anytime we use infinity as an endpoint, it's always, the interval is always open. Infinity is not a number. It can't be included in a set of numbers. And we can use sets that go infinitely to the express sets going infinitely to the left by using minus infinity. Okay, let's just talk a little bit more about intervals, and then that'll probably be good for today. We can draw pictures of sets of numbers, right? So here's a picture of the interval 1, 5 open on the left and closed on the right. And the way we do this is if an endpoint is open, we'll use an open circle. If the endpoint is closed, we'll use a closed circle, like this red circle over here at 5. And then we'll just kind of color in all the stuff in between somehow. So on a computer, I can do it in a different color. Excuse me, with a pencil, you can sort of scribble over it or something like that. Here is the graph of the open interval from -2 to positive infinity. So I have an open circle here at -2 because that's not included. And if the interval is infinite, then I just kind of shade all the way to the right or all the way to the left as appropriate. The entire number line qualifies as an interval. It looks like this, which is a little bit odd, but still accurate, right? It's all the numbers that are between minus infinity and infinity, as it were. And we'll use this double struck R symbol as well to stand for the set of all real numbers. And the set of all real numbers, that's sort of our playground. Those are the only numbers that we'll be interested in. So no complex numbers, for example, in this class. All right, real quickly, one last thing. If we want to take two intervals and kind of stick them together, right? So you can see over here where I'm circling the cursor, I have a graph of the interval from 0 to 2, the open interval from 0 to 2. And then over here on the right, I have the open interval from 5 to 6. If I want to communicate the numbers that are between 0 and 2, and also the numbers that are between 5 and 6, we'll use this U symbol to sort of glue the intervals together. So this is a set union for folks who have seen set theory before. So this is the union of 0, 2, and 5, 6. All right, so this is kind of a precursor to domain and range, which is the main topic of this section, but won't take too long. So I'm already getting close to 30 minutes on the screencast, so I'm going to stop recording here. Take care of yourselves.